This is the Putnam problem that inspired the design for the cover of my book, Learning Isn't Linear. Just for the beauty of pure art, I decided to inscribe a sphere inside the cone along with the cube. Then I added an ellipsoid on top, a tangent plane, and finally a helix with tangent vectors all made in Inkscape. After publishing the book on Amazon, I needed to create some short promo videos. I wondered if it was possible to recreate this design in GeoGebra 3D. I quickly found out that the addition of the inscribed sphere would make this an A2 Putnam problem. By the way, by packed, we mean tightly packed. The sphere and cube are inscribed in the cone tangent to one another. So this is problem 142 in my book, 1998 Putnam A1. A right circular cone has a base radius of 1 and height 3. The cube is inscribed in the cone so that one face of the cube is contained in the base of the cone. What is the side length of the cube? In this video, we won't go over how to find the side length of the cube, because that solution will be found in my book, Learning Isn't Linear. But we will go over everything else, the engineering and programming of the design into GeoGebra 3D. Today we're going to be learning how to construct this geometric design from my video, Learning is Not a Straightforward Process. Okay, so let's just get into it. So here on the side, on the left-hand side, you have algebra and tools. For algebra, you can write algebraic equations, which create the geometric objects in the XYZ plane. And then if you go to tools, you can create the geometric objects in the plane themselves without having to write the algebraic equations. Okay, so the first thing is we want to make the cone. So let's do that. So we can go down here to cone. Now we want to read this. It says cone, select bottom point, then top point, then enter radius. Okay, so first we want to select the bottom point, and then we want to select the top point, and we want to enter the radius. So in the Putnam problem, the height of the cone was 3 and the radius is 1. And we can place it wherever we want in the XYZ plane, but it's probably easiest to center it at the origin. So now we simply created a cone with a height of 3 and a radius of 1 at the origin. Let's now learn how to construct a simple cube in XYZ space in GeoGebra 3D calculator. So if we go to Tools, and we can just go to Cube, it's right here. Again, let's read this. So Cube, select 2 points or other corresponding objects. Okay, so let's put some grid points on the plane, and we can pick one point here, pick another point here, and we've created our cube. All right, so we're just gonna type some stuff into Desmos to try to figure out what those 2 points should be for the cube to inscribe them in the cone. So this is important, watching this, being able to type these numbers into Desmos. So now we're looking at an overhead shot of the cone. We're just making the circle center at 0 with radius 1. And we're just looking at the 2 points that we should have for our cube. And of course, we can change the size of the points, we can change the colors. We input those 2 points to make the cube, but unfortunately, the cube is not inscribed in the cone. So pause the video for a second and try to figure out what went wrong. Okay, congratulations. If you figured out that we made the side length of the cube a distance d instead of s, you got it correct. So what we did wrong is that we made the side length of the cube d instead of s. Those other sides are s. So what we need to do is make the side length s, and now we need to find what those other sides of the triangle are. So we have a right triangle with 2 congruent sides. So we just need to divide by radical 2 to get those sides. It's a 45 degree triangle. Now we have the correct 2 points for the cube to inscribe in the cone. So let's do that. So we see that now we have the cube inscribed in the cone as it should be. Okay, so now we want to find the radius of the sphere and the coordinates of the center inscribed in the cone with the cube. Okay, so we've taken a particular cross section of the cone with the cube and the sphere, which makes a circle here. All right, so we know that the height of the cube is s, and then this length here is going to be s radical 2 over 2. How do you see that? Well, let's look at over an overhead shot. So this is an overhead shot of the cube. So if the side lengths are s, then the diagonal, so this blue diagonal here, is going to be s radical 2. And so this line segment here is just half of that. So we're just dividing by 2. Okay. So we have those two measurements. And now we're just going to mark off our radius. Remember, if the radius circles tangent to a line, then the radius is perpendicular here. So we have two right triangles, okay? So they share the hypotenuse in common. These two sides are congruent. So by the hypotenuse leg theorem, we have two congruent right triangles here. And so this side is also s radical 2 over 2. All right, so let's keep going. So let's just call this line segment here C. And now let's look at this big blue triangle here. Okay, so let's take that out. So it has a base length of 1, a height of 3. And by using the Pythagorean theorem, we get the hypotenuse is square root 10. Okay, so that's good. Now let's look at, well, let's first label this side R. We'll use that later. And now let's look at this little triangle here, this other little right triangle. So we'll also take this out and analyze it. So it has side length S, and then the base is going to be 1 minus s square root 2 over 2. And now, again, we can use the Pythagorean theorem to find r in terms of s. So we find that r is the square root of s squared plus 1 minus s square root 2 over 2 squared. Okay, so that's good. We have r in terms of s, which is what we want. All right, and then there's one more right triangle we need to analyze. So we look at this blue right triangle here. Okay, so we take that out. The base is r, the side length is c, and then the hypotenuse is 3 minus r minus s. Okay, and again, we want to apply the Pythagorean theorem, and this is the equation we get. And now something nice happens. You see that we can replace c with these components here because the sum is equal to the parts, right? C plus s radical 2 over 2 plus r equals square root 10. So we can replace that. And then we get this equation. And we also have that r. So then when we solve this equation for r, for small r, the radius of the sphere, so the final result is that the radius of the sphere is this expression here with r equal to this in terms of s. Okay, so I think it's best to leave it like this because it gets kind of messy. Maybe it simplifies to something. If you want to leave something in the comments about if this simplifies to a nice expression, but otherwise this is fine to leave for putting in GeoGebra. Okay. Okay, so one nice thing about Desmos is that, well, its expressions are typed in LaTeX, and we can type them. You type the expressions in Desmos and then copy and paste them right into GeoGebra, which I think makes it a lot easier. Okay, so I can take this expression here, highlight it, Control C. Okay, we already know what S is, so I can just put that there, hit Enter. That's good, and come back. Now for here, I put r sub c because in Desmos, r has to do something with polar coordinates. So I just did that so that you see the number here. Okay, so I'm just going to take away the c. And I'm just going to copy and paste this, Control C. So I'll put this here, hit enter. Okay, good, it gives me a number. Okay, and then this K here will give us the Y component of the coordinates for the center of the sphere. Now we can construct the sphere inside the cone. We can inscribe the sphere inside the cone. So let's just let K equal to R plus S, enter. And now let's write the equation for the sphere, x squared plus y squared plus, and now we're going to have z, it's just moving in the z direction, so minus k squared equals little r squared. Okay, and we just hit enter. And if we want, we can change the color of it. We can make it green. Okay, so we've inscribed our sphere inside the cone with the cube. All right, so now we want to go over how we can construct the tangent vector to the curve, which in this case is the helix we saw in our diagram. So there's a direction to the path via the parameter t, which is usually time. The tangent vector looks like this. It's like the tangent to a curve, has a magnitude and direction. Now, we also have the position vector, which points to a point on the curve. It starts at the origin, its tail is at the origin, its head is a point on the curve, okay? And then the tangent vector is actually the velocity vector. So we're taking the derivative of the slots of the position vector, okay? Now the problem is, how do we implement this into GeoGebra 3D? It's not so simple. If we just take the derivative of the position vector, we'll get the tangent vector. The problem is it'll be positioned at the origin. It won't be positioned at that purple point, which is what we want. So how do we go about this? Well, we want the u prime, the velocity vector, the tangent vector. So if we're going to use the vector function in GeoGebra 3D, then what we need to do is we need to look at u plus u prime, okay? Because u, the position vector, is pointing at the tail of u prime, and then u plus u prime is pointing at the head. So that's exactly what we want, okay? So that's the head and the tail. And then the two green vectors is what we want to implement into GeoGebra 3D. The GeoGebra calculation. So one of the two vector functions in GeoGebra 3D, you create a vector by putting in the tail and the head. So we can put in u, the position vector, and then we want to put in u plus u prime. Don't put in just u prime into the second slot. You can try it and see what happens, but you won't get the right output. So we have these two vectors here, the tail and the head. We want to put those into the vector function in GeoGebra 3D, okay? And then in our case, we're using the helix. It's given by this expression here. And then to take the derivative, to get the tangent vector, we just take the derivative of each slot individually, the x, y, and z slots, okay? All right, so now what if we want to make a unit tangent vector because the original vector is too long? Well, we can just take the original vector and divide by its magnitude. That's what's in absolute values, okay? And it's given by this, it's just the distance from the origin to the head. And I've done this calculation for you in case you don't know the trigonometric identities. So we actually end up getting a constant. It's not a function of t. So we get this simple number here, and we can use that and divide by our vector. So our final product is the function we put into GeoGebra 3D. We put in vector, then the tail, which is the first slot, we put in the position vector u, and then the second slot, we put in u plus w. All right, so here's the line of code in GeoGebra 3D for the tangent vector. So you see it's vector, and then it has these two slots in it. Okay, so this is the tail, which is the position vector. And then here, this slot here is the head. So you see here, we just added the position vector to each of the components of the velocity vector. Okay, so now we want to construct the ellipsoid, which is on the point of the cone in this geometric structure. We're just using the general equation of an ellipsoid. Um, Here, I just played around with the numbers to get the ellipsoid in the position I want it in, and then the size I wanted it to. So depending on whether you divide x squared or y squared or z squared by some number, it'll change the fatness or the thinness in the different directions. And then of course, the x squared and the y squared, I can just leave those alone, but z, I needed to move up by 3.5 units. All right, so let's go over now the last few things. So how do we make this A point here move? How do we make the B point and the A point? Well, the B point is stationary. That's this point here, N, okay? So I can click it on and off. It's stationary, it's constant. But A is moving. A is moving as a function of M, okay? So if I move M, then A is moving, okay? So where's that here? So here's M, okay? So here's the expression for M. All right, and then the last part is how do we make this little plane here, or as my brother liked to say, the graduation cap? That has to do with this surface function here. All right, so now we're going to look at the surface function on GeoGebra 3D calculator. Okay, so if I go right to this line here, I can start typing in surface, and then this comes up, and then I have three choices. For our purposes, we're going to choose this choice for making the plane. Okay, so I'm just going to expand this out. And you see it's pretty long, okay? It's pretty long. So you see there's three slots here, expression, expression, expression. Those are for the x, y, and z functions for the surface, okay? And then the parameter variable, so all these expressions here have to be in terms of parameters u and v, okay? So here you put u, and then the start and end value will be the lower and upper bounds, and then parameter value here you put v, and start and end value again would be the lower and upper bounds. Okay, so we want to see how the surface function creates a plane in GeoGebra 3D. So in general, a plane in x, y, z space is given by this equation here, ax plus by plus cz equals some constant d. Okay, and the surface function is parameterized by these variables u and v. Okay, so the three slots x, y, and z are really functions of u and v. Okay, so for the purposes of making a plane, we can simply let x equal u, y equal v, and then z equal to some combination of u and v, some linear combination of u and v, and then plus some constant. If if c equals 0 and z is homogeneous here, then the plane will go through the origin. Otherwise, if c is say 2, the plane will be moved up 2 units. Once you have everything together, then you can just play the animation button here. It's similar to Desmos, although not as streamlined yet as Desmos. So if I just click the play button, then we see the vector going around the helix. And then you can also take this plane here and spin it. Okay. And I could also change P here. If I change P, then the helix changes as well. Just give you guys a look at the full line of code. So as was mentioned previously at the beginning of the video, the process may not seem so glamorous, but finding the solution to a hard problem after many failures and attempts is so exhilarating. Alright, till next time. And remember, prioritize long-term learning over short-term test taking.